Okay, greetings, calculus students, and welcome to the first podcast for the AP Prep. Just a couple of quick reminders about the purpose of this. The purpose of these podcasts is for you to be able to understand some of the key or essential concepts from each chapter that we covered. The purpose is not to go through and reteach everything to you. What Mr. Naus and I are going to try to do is to give you some key ideas that you may need to go back and look at in your notes or the textbook, that specifically related to the AP exam. We've done a lot of analysis of previous APs and have a pretty good understanding of what types of things are most likely to occur on the AP exam. So the purpose of the podcast is really just to help you get some information back into your brain, so to speak, to help you be more successful on the AP exam. And this is not the end all of each chapter. Okay, I'm going to talk about chapter 1 with limits and some key ideas with limits. What is a limit? A limit is an intended height of a function. Okay, so it is not the exact value of the function. One of the key ideas, probably the most important idea from chapter 1, is the limit existing versus a function existing. Okay, so a function can exist, but a limit cannot. A limit can exist and a function cannot. They both can exist. They both could not exist. And we had some handouts and spent quite a bit of time in chapter 1 talking about specifically why a limit would not exist. We talk about being DNE. This function has a limit that does not exist at C because the function height does not approach the same value from both the left and the right as you approach C. The real idea here is that you've got to come from both sides, unless it's a one-sided limit with the x approaches C to the right or x approaches C from the left. If it's one of these, then the limit would exist. However, if we're talking about an overall limit, the function must approach the same height from both the left and the right in order to exist. So here's a case where the function does exist because we have a filled-in hole, yet the limit does not exist because we are not approaching the same height from both the left and the right. We also had a situation, if we take a look at this situation, in the second graph that I've just drawn, the limit does exist. The function does exist, but the limit and the function do not have the same value. So the function is approaching the same height from both the left and the right, so the limit exists. The function has a filled-in point, so the function exists, but those two heights are different. So this was a common situation that you're likely to see on the AP as well. We also have the situation of the asymptote, where the function is approaching an asymptote but never reaches an asymptote. In this situation, the function does not exist. The limit technically does not exist, but because it is approaching positive infinity from both the left and the right, we would say that the limit as x approaches C for this function would be equal to infinity. It's simply a more specific way of talking about why the limit is DNE. So we have three pictures that get at the heart of the idea of a limit existing versus a function existing. One of the things we guarantee you'll have to do to some extent on the AP is evaluating limits. So we've looked at a couple of graph situations, also looking at tables, and then equations. Okay. For graphs and tables, what we're looking for is that height value approaching the same side from both the left and the right. The equations, we had a variety of techniques for this. Direct substitution is something that we should always try first if we're asked to evaluate a limit and given the equation. We take the value we're trying to get close to, plug it into the equation, and if it gives us an answer out, then we've got our answer for the limit. Most often, however, and usually on the AP, direct substitution does not work. So the question becomes, what do we do then? Okay, so if direct substitution does not work, we have some other techniques. We have factor and reduce. We have polynomials involved, trying to find common terms, factoring, and reducing. Rationalizing the denominator or numerator. Multiplying by the conjugate. 3 special trig limits. And usually one of these 3 pops up on the AP each year. Not a guarantee, but a high likelihood. And so there were 3 special trig limits that you want to go back and take a look in Chapter 1 at to figure out those answers without having to do anything else. So we've got a variety of ways of evaluating limits, most often by equation, but also with graphs and tables. Okay. There are a couple different types of discontinuities. We had removable versus non-removable. So there's some good information in Chapter 1 about the difference between a removable and a non-removable discontinuity. And that leads us really into the other main of Chapter 1, which is the idea of continuous. Is a function continuous or not? In layman's terms, what we're talking about is being able to draw the function start to finish without picking up our pen or pencil. If we have to pick it up to make a jump, go over a hole, asymptote, then our function is not continuous. Piecewise functions are the most common type of problems in which we find functions that are not continuous, and we also deal with issues of continuity in fractional functions as well too, where the denominator is 0 and therefore it leads to an asymptote or a hole. Okay. There's a theorem that the AP loves to ask information about. It's called the intermediate value theorem. It's listed on page 93. In a nutshell, it says that if you have a function that is continuous, you start at a certain height value, let's say -5, and you end at a different height value, let's say 8, and the function is continuous, that no matter how you draw it or what the function looks like, every height between 8 and 5 must be covered on that function, starting at A and ending at B. Because we can't have any jumps or asymptotes, holes. So in this particular picture, every value of the function between -5 and 8 is achieved. We're talking about height values here. Okay. So from A to B, or star to smile, we're looking at a guaranteed hitting of a height between -5 and 8 somewhere in that interval. That's what's known as the intermediate value theorem. Last thing we'll talk about is the idea of limits and infinity. And there's two different types of problems here that we're talking about. In the first type, we have a limit as x approaches a number of a, and the answer comes out to be infinity or negative infinity. In the second type, we talk about the limit as x approaches infinity or negative infinity of a function, and the answer turns out to be a number. The difference here is that in the first case, we're talking about vertical asymptotes, whereas in the second case, we're talking about horizontal asymptotes. Let's get a visual of each one of these. In this situation, the function is approaching some number, c, and the function is either going down towards negative infinity in both directions from the left and the right, or up towards infinity. If you get a situation where the left is approaching negative infinity and the right's approaching positive infinity, the best answer we can give is DNE. So this is a vertical asymptote situation. X is approaching a number. The answer is positive or negative infinity. In horizontal asymptotes, x is approaching the infinity or negative infinity. So what does that look like? We're getting very, very large x values. And as x gets larger and larger and larger, there's a leveling off of the function. It levels off. Whatever height it levels off to, let's say this is 3, would be the answer for the limit. So in this problem, the limit as x approaches positive infinity of the function that I've drawn below would have an answer of 3. Okay. We actually talked about this scenario here in Chapter 3. We had a couple different strategies, top-bottom tie, something that we use to figure out where the location of horizontal asymptotes would be. We also talked about sort of cheating and plugging infinity in for x into the equation, pretending like infinity is a number, even though it's only a concept, and addressing the equation and trying to reduce the equation to figure out if there's leveling off and where it is. What's important and what I always see on the AP every year is that you will be asked a question about the limit as x goes to infinity or negative infinity of a function. What your brain needs to recognize when you see that notation is that it's really just asking you in a disguised way to figure out if there's a horizontal asymptote, and if so, where. Okay, so the idea of limits going to infinity, either x going to infinity or x going to a number and the answer being infinity, is a regular occurrence on the AP. Okay, so what we've looked at is the overall notion of a limit. Big key idea. Limit existing versus a function existing. Because one exists doesn't mean the other has to exist. There's a lot of great pictures in your book and a couple key handouts from Chapter 1. We talked about how to evaluate limits, graphs, tables, or equations. Different types of discontinuities and the idea of continuous, the concept of continuous in general. Function has to be drawn without picking up your pen or pencil. Piecewise and fractional functions are two places where we often see that a function is not continuous. Intermediate value theorem, again listed on page 93, definitely a key AP topic. And the notion of limits and infinity. Okay. So again, that's about 15 minutes. That's what we're going to try to stick to 15 to 20 minutes on these podcasts so that you spend another 15 to 20 minutes on the 2 free response problems that are assigned every night. We're going to do these podcasts every night for the next 2 weeks. Mr. Naus and I will sort of trade off and go back and forth in terms of helping you get some of these key ideas. If any of this sounded foreign to you, please feel free to go back and re-listen to the podcast, but definitely find Chapter 1 notes and handouts from the first semester when we first started the course itself to help you figure out some of these ideas, and then you'll be seeing these things on practice multiple choice questions and in-class activities and practice problems that we assign. Okay? Great.